Computer Science 460, Design and Implementation, Chapter 7 from Sommerville. This chapter looks at object-oriented design, design patterns, implementation issues, and a bit about the open source environment. A lot of this information used to be in Chapter 14 of the 7th and 8th edition, so if you have those editions, that's where you can find it. The 9th edition appears to be a major rewrite, and the 10th edition fixed a lot of the figures, although it messed a few more of them up, so we went with the best available from all the different editions that I've worked with. This one has been left in for a long time, and I thought you still might appreciate it for the beautiful descriptions of the digital revolution. If you don't appreciate the poetry of Donald Rumsfeld, then I guess you can skip ahead to the next slide or go a little bit further. The digital revolution. Oh my goodness gracious, what you can buy off the internet in terms of overhead photography. A trained ape can know an awful lot of what is going on in this world just by punching on his mouse for relatively modest cost. There's also the unknown. As we know, there are known knowns. There are things we know we know. We also know there are known unknowns. That is to say, we know there are some things we do not know. But there are also unknown unknowns. The ones we don't know, we don't know. Great poet and former Secretary of Defense Donald Rumsfeld there. So back to the architectural design. We'll start with a bit of review, and the bit of review concerns object-oriented design. That involves designing classes and the relationships between them. There are 3 steps to this process. Object-oriented analysis, which is developing an object-oriented model of your application domain. The design, which is designing the model of a software system to implement the identified requirements. And 1 and 2 have to do with level of granularity with which you describe the classes. At the analysis stage, you may not be identifying the attributes and operations, but at the design stage, you definitely are. And then object-oriented programming, well, you know what this is. This was CS 151. Basically, a lot of any object-oriented programming language, such as C++ or Java, will get the job done after you have the object-oriented design. And it's permissible to move back and forth to each stage. So you can move to the next stage by refining the previous stage, adding detail to the existing classes, devising new classes for additional functionality, and they're invariably interleaved. And in regard to point 2, software design is a pretty creative activity in which you identify components and the relationships based on the customer's requirements that those can change, and then implementation is the process of realizing the design as a program. There are several advantages to an object-oriented design. Having object reuse from previous systems. Object-oriented design makes changes to the system easier, especially if the objects are loosely coupled. Then, that is, they're independent objects. It makes the reuse much, much easier. And the state representation of an object that's loosely coupled and independent doesn't influence other objects. So you can do this object-oriented design using the Unified Modeling Language, or UML. We already talked about UML in Chapter 5, but just to reiterate, UML stands for Unified Modeling Language. It was created in 1999, and it's part of the Rational Unified Process. The Rational Unified Process is characterized by the fact that it's iterative and incremental. Of course, you don't need to use the Rational Unified Process in order to use UML. And we'll be working with a lot of classes as part of UML since it's focused on object-oriented design. And in case you wanted a definition of an object, it's an entity that has a state and a defined set of operations which operate on that state. The state is represented as a set of object attributes. The operations are associated with the object provide services to other objects which require these services when some computation is requested. Objects are created according to object class definition. The class definition serves as a template for the objects. So you can think of the class as the cookie cutter and the objects as the individual cookies that come out from that cookie cutter. The class includes declarations of all the attributes and services which should be associated with the object of that class. And you'll recall that classes have names, attributes, and operations, and those go in different boxes. Classes can also be arranged in a class hierarchy, where one class is a superclass or a generalization of one or more subclasses. Subclass basically inherits everything from its parent class, but can override those things if necessary. And the other type of relationships are association, which is usually denoted as a line between object classes that can be annotated with information about the association and the cardinality. You know, a doctor sees one-to-many patients in one of the earlier chapters. There can also be more general relationships. Attribute of an object is associated with another object. And finally, you have aggregation and composition, where an object is made up of other objects. So here's a generalization hierarchy diagram. This is copied and pasted pretty well for a change. You can read the arrows going up. A manager is a type of employee. A programmer is also a type of employee. The project manager and department manager and strategic manager are all different types of managers, and they have different attributes that they override down below. So, object-oriented design using UML. So, can you guess the subject of the tutorial? That's right, it's the weather station. And if you want a description of the weather station, you can look on page 22, section 1.33 of the 10th edition. And basically, the government of a country with large areas of wilderness decides to deploy several hundred weather stations in remote areas. They collect data from a set of instructions that measure temperature and pressure, sunshine, rainfall, wind speed, and wind direction. Includes a number of instruments that measure weather parameters, such as wind speed, direction, the ground and air temperatures, the barometric pressure, and the rainfall over a 24-hour period. Each of these instruments is controlled by a software system that takes parameter readings periodically and manages the data from the instruments. So the general design process is understand and define the context and external interactions with the system, design the system architecture, identify the principal objects in the system, and then develop design models and specify the object interfaces. So again, here's a description of the case study. The weather mapping system is required to generate weather maps on a regular basis using data collected from remote unattended weather stations and other data resources such as weather observers, balloons, and satellites. Weather stations transmit their data to that area computer in response to a request from that machine. The area computer system validates the collected data and integrates it with the data from different sources. The integrated data is archived, and, using data from this archive, a digitized map database and a set of local weather maps is created. Maps may be printed for distribution on a special purpose map printer, or may be displayed in a number of different formats. And again, you'll no doubt remember this from chapter 1 of the 10th edition of the book. It's one of 4 case studies that are discussed in the book. So the first thing is looking at system context, and this is a static model that describes other systems in the environment. And you use a subsystem model to show the other systems. And this can be done via simple block diagrams. And the model of system use is a dynamic model that describes how the system interacts with its environment, and that uses use cases to show the interaction. So here's the system context model. You have the weather information system, interfaces with satellite, control system, and weather station. Here are the use cases. You can see that there are quite a few use cases. And take a look at how you structured these if you're putting those together for a document for your project owner. But here you can see the use cases, the different things that entities within the system can do, whether it's the weather information system, the control system. You'll note that they're missing the user here as well, but the control system and weather information system in some way make requests to other the weather station. From there, you write up your use case description. This one is report weather. So who are the actors here? The weather information system and the weather station. You have a description as to what happens, stimulus, and response. And then comments, weather stations are usually asked to report once per hour, but that can differ from one station to another and may be modified in the future. Once the interactions between the software system and the system's environment have been defined, use this information as a basis for designing the system architecture. And the architectural design occurs after you understand the interaction between the system and its environment. Here you identify the major components that make up the system and their interactions. Organize these components using an architectural pattern, such as a layered model or a client-server model or model view controller architecture. And in our case, the weather station is composed of independent subsystems that communicate by broadcast on a common infrastructure. And in general, we discussed several different architectural patterns in Chapter 6. You should try to make your system architectures as simple as possible, and it's good to base them on previously successful ones. As a general rule of thumb, there should be no more than 7 fundamental entities included in your architectural model. And that's due to something known as Miller's principle. Miller's principle is basically 7 plus or minus 2 elements can be stored in our short-term memory. And it has something to do with the sounds that we can keep track of, or the number of sounds we can keep track of. And this also may be due to Jordan's work on programming, which he said something about having no more than 5 different subroutines in order to make a block of code understandable. But in general, keep it as simple as possible. Follow the KISS principle. So here's a high-level architecture for the weather station. You have the fault manager, configuration manager, power manager, communication subsystem, data collection subsystem, and the instrument subsystem. They all interact together via a communication link. So again, you can see we keep this to 7 different components. And each subsystem listens for messages on the infrastructure and picks up the messages that are intended for them and then responds to those messages. You can also do a little bit more granularity by looking at, for example, the data collection and then zooming in and seeing that it has a transmitter, a receiver, and weather data as part of it. And this is figure 7.5 on page 188 of the 10th edition. Next, you go about object class identification. We talked a bit about this in Chapter 6. 4 approaches. There's the grammatical analysis. Objects are nouns. Operations and services are verbs. And attributes are nouns based on the clustering of adjectives into lexical sets. There's the tangible entities approach. These are things in the application domain. For example, aircrafts, jobs, offices, companies, weather stations, etc. Sommerville doesn't talk too much about the third one, which is behavioral approaches. Basically says to look at the behavior of the system and what influenced it. And scenario-based object identification involves identifying and analyzing various scenarios the system use. As you analyze these scenarios or user stories, the team responsible for analysis identifies the required objects, attributes, and operations. If you want to give this a try, pause the presentation, go back and take a look at the weather station description, and try to identify the classes. If not, you can continue ahead with me. Here is Sommerville's solution to the different classes. You have the weather station. Its attribute is identifier, and it has several operations such as reporting the weather, reporting status, restarting, shutting down. Weather data has far more attributes: air temperatures, ground temperatures, wind speed, wind direction, pressures, and rainfall, and it can collect and summarize those data. There's the ground thermometer, anemometer, and barometer, and each one of those has their attributes and operations. This model is from the 9th edition. The 10th edition figure has cleaner lines, but it cuts off large sections of the figure, so I think it's best to see the full figure, even if you have the kind of weird blue background on it. Design models show the objects in the system and the relationship between these entities. They're the bridge between the requirement and implementation phase. It's a balancing act. You need enough detail to implement, but you also want to abstract enough for a product owner to understand. And you can, again, develop these design models at different level of detail. There are really 2 kinds of design models. Structural models describe the static structure of the system in terms of the classes and relationships, And dynamic models describe the dynamic interactions between objects. Examples of design models include subsystem models that show logical groupings of objects into coherent subsystems, sequence models that show the sequence of object interactions, state machine models that show how individual objects change their state in response to events, and other models include use cases, aggregation models, and generalization models. So, subsystem models again show how the design is organized into logically related groups of objects, and in unified modeling language, these are shown using packages, and these encapsulate several related classes. You should be familiar with sequence diagrams and state charts from the previous lecture. Sequence models show the sequence of object interactions that take place. Objects are arranged horizontally across the top. Time is represented vertically, so models are read top to bottom. Interactions are represented by different labeled arrows. Different styles of arrows represent different types of interaction. Then rectangle is an object lifeline and represents the time when the object is the controlling object of the system. So here we can see a sequence diagram. We can see the information system, the satellite communications, weather station, the communication link, and the weather data. And we can see the messages that are passed back and forth in this particular interaction for requesting and receiving a report. State diagrams show how objects respond to different service requests, state transitions that are triggered by these requests, and they're useful for high-level models of a system or to understand the object's runtime behavior. So, for example, here is the weather station state diagram. We saw this type of diagram with the microwave oven and with Harrell's stopwatch in Chapter 6. This one is figure 7.8 on page 193 of the 10th edition. The figure is from 9th edition, as you might surmise from the shading, because the 10th edition cuts off part of the diagram. And, again, state machines are good to summarize the behavior of a single object. As a caveat, you don't have to draw all of these, just the ones that are more complex and that you need to understand the behavior of the system. Object interface specifications specify interfaces so that objects and subsystems can be designed in parallel. Object interfaces have to be specified so objects and other components can be designed together. Designers should avoid designing the interface representation, but should hide this from the object itself. Objects may have several interfaces which are viewpoints of the methods provided, and UML uses class diagrams for interface specification, but you can also just go ahead and code it in your third generation object-oriented programming language. This figure is 7.9 on page 195 of the 10th edition, and it shows how two interfaces can be defined for the weather station. Left side is the reporting interface that defines operation names that are used to generate weather and status reports. The remote control interface on the right-hand side provides 4 different operations which map onto a single method in the overall weather station object. And we talked a bit about design patterns last time, but it's always a good idea to have more exposure to this idea because it's important and it's tremendously useful. And a design pattern is a way of reusing abstract knowledge about a problem and its solution. Pattern is a description of the problem and the essence of its solution. It should be sufficiently abstract to be reused in different settings. For example, client server can be reused in several different settings. Pattern descriptions usually make use of object-oriented characteristics such as inheritance and polymorphism. Patterns and pattern languages are ways to describe best practices, good designs, and capture experience in a way that it's possible for others to reuse this experience, and that's from the Hillside group. So, what do you have in a design pattern? A name, which is a meaningful pattern identifier, problem description, solution description, not necessarily a concrete design, but a template for a design solution that can be instantiated in several different ways, and consequences, results and trade-offs of applying the pattern. So, let's take a look at one for the observer pattern. And the observer pattern separates the display state of an object from the object itself and shows that alternative displays can be provided. When the object state changes, all displays are automatically notified and updated to reflect the change. And This is often used in data visualization. And, in a lot of situations, you do have to provide multiple displays of state information, such as a graphical display and a table-based display. And it's useful in all situations where you have more than one display format. The solution is two abstract objects, the subject and the observer, and two concrete objects, the concrete subject and the concrete object, which inherit the attributes of the related abstract objects. The subject only knows the abstract observer and does not know the details of the concrete class. Therefore, there's minimal coupling between these objects, and because of this lack of knowledge, optimization and enhanced display performances can sometimes be impractical. Changes to the subject may cause a set of linked updates to observers to be generated, some of which may not be necessary. So here's how it would actually work, and this is figure 7.11 on page 197 of the 10th edition. And so this shows how the observer pattern can be used to display the same information in multiple ways. So we have our table with A, B, C, and D. We have two different observers, one of which reflects it in the much maligned pie chart, that's observer 1, and the other which gives it in a bar graph. And the 10th edition has a nice UML model observer pattern on the same page, but it's cut off in the slide pattern, so this one's from the 9th. And to use patterns in your design, you need to recognize that any design problems you're facing, you may have an associated pattern that can be applied. So if you want to tell several objects the state of some other object has changed, that's the observer pattern. If you want to tidy up interfaces to a number of related objects that have been developed incrementally, that's the facade pattern. A standard way of accessing elements in a collection, irrespective of how it's implemented, that's the iterator pattern. Something you've seen in 151 certainly. And then allowing for the possibility of extending the functionality of an existing class at runtime is something known as the decorator pattern. And again, the gamma text will give you some details on these different types of patterns. Implementation issues, section 7.3, tends to be a trickier part of the software development lifecycle, and we'll get to see that a bit in 461. It's separate from programming, but can include programming. And there are three issues that are not covered in most programming texts. These are reuse, configuration management, and host target development. So reuse, most modern software is constructed using existing components. While it sometimes looks easy, it can be difficult to get them to all work together, particularly if you're reusing things from different versions of software or different versions of the language. It can be difficult to get them to work together. Configuration management is if you don't keep track of the different versions, you can sometimes include the wrong version in a build. We'll talk more about this in chapter 25. And host target is basically the production software doesn't reside on the same machine that it was developed on. And that can give you a host of problems if you don't have the right libraries, right operating system, right version of the compiler on the target system. Can create some issues. So reuse levels, there are 4 of them: system, abstraction, component, and object. And from 1960s and 1990s, pretty much we developed new software from scratch, and we wrote all the code in high-level programming language. The only significant reuse was reuse of functions and objects in programming language libraries. Cost and schedule pressures meant that this approach became increasingly unviable, especially for commercial and internet-based systems that had to be frequently updated and had to get to market as soon as possible. Reuse can take place at these 4 different levels. So the abstraction level, at this level you don't use the reuse the software directly, but you use the knowledge of successful implementations in the design of your software. The object level, at this level you directly reuse objects from a library rather than writing the code yourself. Component level, components are collections of objects and object classes that you reuse. And then the system level, you can reuse entire application systems. Now, reuse also has some costs associated. Cost of time spent looking at software to reuse and assessing whether or not it meets your needs. Sometimes you have to buy the reusable components. For large off-the-shelf systems, these costs can be pretty darn high. PeopleSoft, SAP, they're not cheap. Costs of adapting and configuring the reusable software components to reflect requirements of the system, and the cost of integrating reusable software elements with each other. And with the new code that you've developed, the need to write glue code to put these things together. Configuration management takes place in three different ways. Version management. Basically, here you have support to keep track of the different versions of the software component, and it includes these version management systems include facilities to coordinate development by several different programmers. Integration, configuration management for systems. Support's provided to help the developers define what versions of components are used to create each version of the system, and that description is then used to build a system automatically by compiling and linking the required components. And then problem tracking, which are support tools to allow users to report bugs and other problems. They also allow all developers to see who's working on which of these problems and when they're fixed. And configuration management is the name given to the general process of managing and changing software system. The aim is to support system integration so that all developers can access project code and documentation in a controlled way. Find out what changes have been made and compile and link components to create the most recent version of the system. And last but not least, in this chapter we talk about open source development. Our buddy Stallman is pictured here, but he is now looking for a new job. You can still enjoy some of his greatest hits, such as Eating Things Off His Foot and the Free Software song. In case you're wondering why he's looking for a new job, per Wikipedia, in September 2019 it was reported that Stallman had made statements on internal CSAIL listserv in defense of deceased MIT professor Marvin Minsky in relation to Virginia Giuffre's deposition that she was directed to have sex with Minsky by Jeffrey Epstein. By the way, a guy who didn't kill himself. As a response, Stallman resigned from both MIT and the Free Software Foundation. His rider for giving speeches is also probably something that's very, very bizarre, and it's definitely worth a look. Anyway, open source development is an approach to software development in which the source code of a software system is published and volunteers are invited to participate in the development process. Its roots are in the Free Software Foundation, which was started by Stallman, and this advocates that source code should not be proprietary, but should always be available for users to examine and modify as they wish. And open source software extended this idea by using the internet to recruit a much larger population of volunteer developers. Many of them are also users of the code. Best known open source project is, of course, the Linux operating system, which is widely used as a server system and increasingly as a desktop environment. Other important open source projects are Java, Apache Web Server, and MySQL database system. And note that I'm noting here that free software is quite different than the open source movement. You have to be pretty careful in separating them, and the free software movement will get quite upset if you don't get it completely right, so I'll have to let them tell you the difference, or you can look that up. And some things to consider about open source is, should the product that you're developing make source of open source? Should it make use of open source components? Should an open source approach be used for the software's development and licensing? And they're not easy questions. There are three basic types of licenses. The GNU public license. This is the reciprocal license, which means that if you use open source software that's licensed under GPL, then you have to make your software open source. There's the lesser public license, where you can write components that link to open source code without having to publish the source of your components. And then there's the Berkeley Standard Distribution. This is a non-reciprocal license, which means you're not obliged to republish any changes or modifications made to open source code. You can include the code in proprietary systems that are sold. So, you consider those when you're looking at intellectual property rights. And next time we'll be working more on the project. Thanks for your time.